Welcome to our RAG Best Practices Guide. Most RAG implementations work in demos but struggle in production. The gap isn't technical sophistication, it's systematic discipline across content, retrieval, trust, and operations. We've compiled years of production RAG experience into this comprehensive guide. Let me walk you through the 5 critical areas that separate working RAG from reliable RAG. Chapter 1: How to build RAG systems that pay off. If you ask 5 teams what RAG is, you'll get 5 different answers. Some think it's just adding a vector database. Others think the model magically reads their documents. This misalignment leads to architectural mistakes that compound over time. Here's what RAG actually is: a pattern where a language model generates answers based on information retrieved at runtime from an external knowledge source. The key word here is retrieved. The system doesn't expect the model to know your data. It finds relevant information first, then asks the model to reason with it. Think of it this way: search, then think. The model isn't the explorer. It's the analyst working with documents you hand it. If retrieval is weak, generation will be confident and wrong. If retrieval is noisy, generation will sound plausible but vague. Every RAG system begins with content, documentation, policies, manuals. None of it is AI ready by default. Before retrieval happens, data must be cleaned, chunked, and embedded. When a user asks something, the system retrieves relevant chunks. This step determines what the model sees. At this point, the system has already succeeded or failed. The model just hasn't spoken yet. RAG systems fail quietly. Teams test whether answers look good, but rarely test whether they retrieve the right information. Chunking decisions get made once and never revisited. Prompts become brittle, and production realities like changing documents, access control, and latency get ignored until it's too late. Chapter 2: Why your RAG keeps failing. In production RAG systems, content quality is the dominant factor behind accuracy and reliability. While teams focus on models and prompts, most failures originate earlier in the pipeline. In proof of concept systems, content gets collected, embedded, and forgotten. This works until it doesn't. Real-world knowledge changes. Documentation evolves. Policies get superseded. If your RAG system doesn't account for this, retrieval quality degrades gradually. The system doesn't crash, it just becomes unreliable in subtle ways. Data quality issues rarely show up as obvious errors. Instead, they surface as reasoning flaws. The system retrieves broadly relevant content but misses critical constraints. It merges sources never meant to be combined. It answers confidently while being slightly wrong. Metadata is one of the most underutilized tools in RAG. In production, metadata directly influences which knowledge the model sees. It enables filtering by role, prioritizing authoritative sources, enforcing access control, and handling time-sensitive information. Chunking is often done mechanically based on token limits rather than meaning, but chunking determines what the system can retrieve and how it reasons. Poor chunking fragments explanations, separates rules from exceptions, forces the model to infer missing relationships. Production systems use multiple chunking strategies depending on document type. The goal isn't uniform chunk size, it's retrievability with context intact. Here's the key insight: improving content foundations delivers larger gains than switching models or tuning prompts. Strong content, metadata, and chunking reduce downstream complexity and make every other component more effective. Chapter 3: Why your RAG hallucinates. Retrieval quality sets a hard ceiling on answer quality. If the right information isn't retrieved, generation cannot compensate. Despite this, retrieval is often treated as an implementation detail. The critical reframe is this: retrieval is the product. Retrieval issues are hard to detect because they rarely produce obvious failures. The system responds fluently and confidently. Answers are close enough to be convincing. Over time, these near misses accumulate. Users notice inconsistencies, edge cases fail, trust erodes. There's no single definition of good retrieval. The balance between recall and precision depends on your domain, the questions users ask, and the cost of being wrong. This is why real query evaluation matters more than abstract similarity metrics. Embeddings provide powerful semantic representation, but they struggle with domain-specific terminology, procedural steps, and precise constraints. Production systems layer additional techniques on top: metadata filtering, hybrid retrieval, re-ranking. These transform retrieval into a domain-aware capability. Hallucinations are often framed as a model problem. In practice, they originate upstream. When retrieval returns weak or conflicting context, the model fills gaps with plausible assumptions. This isn't a flaw. It's expected behavior from a system designed to generate coherent text from incomplete evidence. Here's a counterintuitive finding. Passing fewer, higher quality sources to the model reduces hallucinations more effectively than expanding context windows or refining prompts. Less context, better chosen, outperforms more context, loosely selected. Retrieval quality degrades as content evolves. Without monitoring, systems drift. Signals like increased answer variance, growing context sizes, and user corrections are early indicators. Teams that instrument retrieval from the start can detect and fix issues before they reach users. Chapter 4: Building Trustworthy RAG. As RAG moves into production and supports real business decisions, trust becomes more important than fluency. A system that sounds confident but can't validate its outputs is a liability, not an asset. RAG improves factual grounding, but it doesn't guarantee correctness. Models can misinterpret context, overgeneralize from partial evidence, or fail to recognize missing information. The most damaging failures aren't obvious errors. They're subtle inaccuracies delivered with confidence. Self-reflection refers to system behaviors that evaluate outputs before they reach users. This includes checking answer consistency with sources, estimating confidence, validating claims against retrieved context. These steps add latency, but significantly improve reliability. Self-reflection isn't about making the model smarter, it's about making the system more cautious and accountable. One of the strongest trust signals is the ability to decline answering when confidence is low. This requires detecting insufficient retrieval, conflicting sources, or ambiguous queries. In high-risk domains like legal, medical, or financial applications, refusal isn't optional, it's required. A system that admits it doesn't know something earns more trust than one that always produces an answer regardless of evidence. Feedback is often collected but rarely integrated effectively. For feedback to improve a system, it must be tied to specific interactions, including retrieved sources and system decisions. Not all feedback is reliable. Users may misunderstand, disagree for subjective reasons, or provide malicious input. Mature systems apply weighting, validation, and review processes before incorporating feedback. Trustworthy systems learn cautiously, not reactively. Investing in trust mechanisms has clear ROI. Systems that can explain outputs, acknowledge limitations, and improve from structured feedback retain user confidence over time. Those that can't tend to be quietly abandoned despite significant investment. Trust infrastructure is also a competitive differentiator in enterprise contexts, where procurement and compliance require demonstrable reliability standards. Chapter 5: Operating RAG in Production. Deploying a RAG system is only the beginning. In production, systems must be evaluated continuously, failures must be traceable, and operational constraints shape architecture. Offline evaluation validates early assumptions, but it doesn't reflect real usage. Once deployed, query patterns evolve, content changes, user expectations increase. Production evaluation combines automated signals, periodic human review, and business-level metrics. The objective isn't maximizing a single score. It's detecting degradation early and understanding why it's happening. RAG systems are multi-stage pipelines. Failures can occur during query interpretation, retrieval, ranking, validation, or generation. Without tracing, these failures are nearly impossible to diagnose. Effective tracing captures decisions, not just outputs. It records which documents were retrieved, how they were ranked, what context was passed to the model, which validation steps were applied. This visibility enables systematic debugging. In mature teams, incorrect answers are treated as incidents, not anomalies. Each failure triggers analysis of retrieval quality, content health, validation behavior, system configuration. This transforms failures into structured learning opportunities. This mindset shift from anomaly tolerance to incident response distinguishes teams operating reliable RAG from those managing unstable ones. Production systems must balance quality with cost and latency. Validation steps add overhead. Larger contexts increase inference cost. Retrieval strategies affect response times. These trade-offs should be addressed explicitly during design. The most effective teams establish baseline metrics before optimizing. Without baselines, there's no reliable way to know whether a change improved the system or just shifted costs. RAG systems often expose sensitive internal knowledge. Access control must be enforced at retrieval time. Metadata-driven filtering ensures only authorized content reaches the model. In many real-world security incidents, issues trace back to retrieval design, not generation behavior. A RAG system isn't done when it answers questions correctly once. It's done when it can be trusted, observed, and improved continuously. Production readiness isn't a milestone. It's an ongoing commitment requiring clear ownership of content quality, retrieval health, evaluation processes, and operational metrics. Closing thoughts. Let me leave you with the core principles. RAG is a system design discipline, not just a feature. Content quality determines retrieval quality. Retrieval defines the ceiling for generation. Trust requires validation and restraint, and production reliability requires continuous evaluation, tracing, and clear ownership. The gap between a RAG system that works in a demo and one that delivers value in production isn't primarily technical. It's about systematic discipline across every layer. Get in touch if you're building RAG at scale and want to ensure these fundamentals are in place. Thanks for watching.